Hello, everyone. Yes, yes, I'm ready. Yes. Hello, everyone. Welcome to a live session on this course on signal processing, algorithms, and architectures. This is Dr. Anirban Dasgupta. I'm an assistant professor AAA Department, IIT Guwahati, and today I will take up questions which you have come across while listening to the lectures. I'm sure you had a wonderful learning. Let's see. So please feel free to watch and I'll give you. So you can use the Excel sheet to post your questions. Also, you can post your question in the live YouTube comments so that I'll be addressing your queries to the best of my knowledge. So, one thing I would like to discuss with you regarding signal processing and your uh, machine learning, which is now all people are talking about. So, you can see the birth of machine learning kind of originated not only from mathematics and statistics, but also from signal processing. A lot of concepts which are covered in this lecture uh, have influenced the birth of a lot of machine learning algorithms. But generally, I see most of the students are afraid of taking signal processing courses, or rather, afraid of the course signal processing, mainly because they're afraid of the maths of the signal processing. But if you see closely, signal processing is not a rocket science, it's a very simple thing. And the better you practice, you will get better at signal processing. Now, there are several approaches in studying signal processing. One is a core theoretical approach, and one is an applied approach. So code theoretical approach requires you to solve a lot of numericals, lot of problems to get better at the concept. So there are some recommended books which I have suggested, like the Digital Signal Processing book by Prof and Manolakis, and also by Professor Alan Oppenheim. So these books have a lot of exercises and examples. If you practice them, you will really get better at signal processing. Now, again, the applied side is also very important, like how you apply these signal processing algorithms to solve a real life problem. Like say you have a noisy signal, maybe you are listening to my audio, but your audio quality is not good, it's filled with noise. So what you can do is you can apply some filtering technique. Now, which filtering technique you should be using, that highly depends on the type of noise. So hence, a good exposure to applied signal processing is also necessary. Or say you want to do some kind of speech to text synthesis or extract some segment of speech where repeating patterns are there. So in such kind of applications, I have given examples of pattern matching where we have used dynamic time warping. So all these applied signal processing stuff requires you to do a lot of coding. So you have to have a good balance of good coding skills, and it need not be coding in languages like C++. You can easily do these kind of applications in Python or MATLAB, which are easier to develop. And it's a good to have a blend of a very strong mathematical foundation as well as your coding skills, so that you can really have a good grasp of signal processing. So those who are watching this live session, I request you to post your questions and queries. So one good exposure to signal processing is again uh, not just exploring from the way you have the signal ready with you, but also you should have some experience or exposure to the capture of these signals. And the very reason being that you will learn a lot of concepts regarding analog signal processing, which is also a very important tool in signal processing, but also about the signal acquisition. And that will help you understand discrete time or digital signal processing to a great extent. Like, for example, any physical quantity which can be sensed can be finally converted to a digital signal. And the reason behind this is the power of sensor technology. So what is a sensor doing? Sensor is basically converting energy in any form to energy in electrical form. And why electrical form? Because electrical energy has a lot of advantages with respect to storage and transmission. So the sensor captures, say, a physical quantity, like in the example of temperature sensing, which was typically the first lecture of this module. So there we discussed how a temperature sensor uh, captures a variation in the temperature, the ambient temperature, and then converts it into either a current signal or a voltage signal. And you might have heard of sensors like RTD, thermocouples, thermistors, which have different behaviors. And end of the day, you get a voltage signal. If you get a current signal, you can use a voltage current to voltage converter, finally get it to a voltage signal. Why do you need a voltage signal? Because when you give this input to the ADC, that typically is a voltage input. So there is a ground pin and there is a analog pin. Again, the ADC typically has voltage levels kind of from 3.3 volts or 5 volts. So if your signal is not in that range, if the signal is in millivolt range, then your quantization will be heavily affected. So for that, you need to do some kind of amplification. I also discussed something on the signal conditioning part, that is the anti-aliasing filter you might be using if your signal has high frequency noise. That can be filtered out, and not only that, your Nyquist rate will be obeyed. So these constraints, if you do it practically, and these are not very expensive components, you can get them in very low cost. You can even capture the signal using simple components like an Arduino and some sensors like DHT11, and you can get a stream of the analog temperature data. Now, these sensors are good for your lab experiments so that you get a good understanding. They may not be very accurate, and the sensor noise may be very huge. Sensor can have a poor SNR, but still it is good for you to get started and understand the generation of the signals. Now, you can make this as a hobby and purchase a lot of sensors, interface with your board like Arduino, which are very easy. Early days, interfacing was a big challenge, specifically with your 8051 microcontrollers, because you needed to interface a separate ADC, and the circuits were in breadboard in a complex manner. So now things are much easier to do. So I request you to start experimenting, because practical experience gives you a much better understanding. So feel free to ask your doubts because I'll be there for half an hour more. So utilize this time to interact. Whatever doubt you have, any queries, uh, any suggestion for books or research papers, I'll be happy to help you. So one of the most interesting concepts which I had encountered in this course is uh, in the architecture domain is the signal processing architectures, which is the pipelining concept. So it's neither strictly serial nor strictly parallel, but it's a blend of both worlds. And I think pipelining is a wonderful technique which is developed, which is really interesting. And once I was deriving the relationship or the complexity of linear convolution, and if you see in the linear convolution operation, if your signal has length of L and your filter has a length of M, then your output sequence is having a length of n plus m minus 1. If you see closely the pipelining thing, it's also the number of clock cycles becomes n plus L minus 1, which is similar to convolution. It's the same as convolution. So if you see the pipelining structure that it first hits a single stage and then proceeds with a good overlap and goes through the overlap and slowly goes out of the overlap. It's exactly the same as convolution. So this is one example where you see that two different, entirely different things or concepts in signal processing. One is convolution and one is pipelining. One is a software concept, one is a hardware concept. They have a very good analogy with itself. So in this manner, many concepts in signal processing has a very good analogy, not only with other signal processing concepts, but with many other concepts of engineering. So if you can understand the philosophy of one concept very nicely, it becomes very easy to understand a similar concept with a similar analogy. This convolution operation and correlation operation is also very useful in understanding the basics of deep learning, which are convolutional neural networks, because the operations are kind of very same. Only thing is that in signal or image processing, you have a fixed convolution mask. Of course, in deep learning, you also have a fixed mask which is trained from the data. So during the training process, the mask is not fixed, it's learning from the data. But once the training is over, your convolution mask is fixed. And the operation is the same as your classical signal processing operation. So many concepts in AI use the basics of signal processing or the fundamentals of signal processing, and in particularly statistical signal processing. So what these methods I have discussed in this course was mainly your classical or this like deterministic signal processing, but there are many examples where your stochastic signal processing applications are used, which are extended in such a way that they are very useful in AI and ML algorithms. They are kind of the genesis of those algorithms. another interesting aspect I would like to say about signal processing is embedded signal processing or signal processing on hardware. Now, I just discussed at the start of this live session about how you can capture a signal from a sensor, which is typically an analog sensor. You get an analog signal, you do some kind of signal processing, signal conditioning, which is also a part of analog signal processing. And then you get the signal to some microcontroller board like Arduino, where you get the stream of signal. And that gives you a very good idea about your sampling rate. But then, not only that, if you can do some simple operations on those signal streams, typically in real time, that gives you a very good notion of embedded signal processing, because now you're not doing a signal processing on a stored CSV file on a PC, and using Python you are loading the file and say you're using the operations, but rather you're doing things in real time on a microcontroller. So why that is important? Because there you have resource constrained environment. You have very small amount of RAM, and your processing power is also very small. So in that constrained environment, if you can solve a signal processing problem, which can be as simple as denoising by a low pass filter, then that will give you a very good grasp of how signal processing can be useful in real life. And not only that, if you can really solve a real world problem, you can come up with a product idea, and you can actually think of a solution and work on that, develop on the accuracy of your algorithm, and maybe you can take help from some machine learning inputs to the system, and maybe you can go for a better device like a Raspberry Pi kind of a thing. And finally, you can come up with a very good solution which has a potential to become a product. And you never know if that technology works well, it can be a realistic product in the future, provided there is substantial market and the technology is good enough. So end of the day, signal processing can also bring you money in that sense. That a lot of recent products use signal processing, or you can say a blend of signal processing with machine learning. And that is why this specialization, signal processing and machine learning, in short known as SPML, is very popular these days. Many people are taking this as a career opportunity. And again, I want to repeat that signal processing and machine learning are not very separate entities, but they play hand in hand. Signal processing is more of having analytical function where you have your X, you apply those analytical functions on this signal f of X, get your output Y. Whereas machine learning is to find the best function f from your data X and Y. So it's kind of a learning process. So if you think of this philosophy, signal processing and machine learning coexist in today's world. So if you are looking into some recent topics of signal processing, then graph signal processing is something, although it's not very new, but it's a topic you can always explore. It's really exciting and it's useful in many applications, specifically, for example, seismic signal processing and train signal processing, EEG signals. Graph signal processing has been playing a very important role, and a lot of problems are being solved using graph signal processing. Signal processing also has a good relationship with your information theory, and again, there are a lot of concepts in information theory which are also used in signal processing. End of the day, you are trying to extract information from the signal. Like, for example, there is a physical phenomena happening, such as maybe there is a volcano, or maybe the speech signal, somebody wants to express something, there is some kind of malicious intent in the speaker or in the audio signals, which you have to decode. So end of the day, how you are trying to extract the information from the signal is the whole core job of signal processing. So audio signal processing is very important in such scenarios where uh, you can take a lot of cues from the audio. Then image processing is, you can say, a very big derivative of signal processing. And image processing altogether is a big subject where there's a lot of scope, a lot of research problems, which still people are working on. It has a lot of industrial applications. So in this course, I tried to not only give signal processing algorithms and architectures as a concept, but here a lot of related concepts which you typically study in electronics and electrical engineering have been used. For example, uh, the architecture portion, I've discussed about your barrel shifter. Now this barrel shifter is a combinatorial circuit, unlike your regular shifters, which are your sequential circuits made up of kind of flip-flops. So these concepts needs to be refreshed while you try to study the architecture part. Then this ADC has some concepts of sensors, then quantization, which are very essential parts of not only signals but also some instrumentation, like the resolution of an ADC, and that's the number of bits it requires, the sampling rate of the ADC. So sampling rate defines your time sampling, whereas your resolution is defining your amplitude quantization. So when you want to buy an ADC, these two specifications you should be looking at. You should be very keen on having these two specifications correct. Then the concept of watchdog timer in a digital signal processor comes from the concept of embedded systems, or specifically microprocessors and microcontrollers. So this watchdog timers helps your system to get periodically reset whenever there is a there is a problem. So it triggers a reset. So these are very useful hardware components which gets you a revision from those concepts of microprocessors and microcontrollers and embedded systems in general. Then it also has concepts from communication, specifically embedded communication. For example, if you are using communication like I2C, I2C is an inter-integrated circuit. So there is a serial clock and a serial data. So whenever you have a clock, that means it's a synchronous communication, which is unlike UART, where it's an asynchronous communication. Now, why these are important? Because if there is requirement to maintain uh, sampling rate, so your data communication or your signal communication, if you're using something like an asynchronous method, then there can be a lot of problems. So there are a lot of concepts in signal processing which are typically not considered classical signal processing, but more of applied signal processing, like your zero crossing detection and peak detection. So they play a major role in many signal processing applications. For example, in biomedical signal processing, estimation of vital parameters like your heart rate, your respiration rate. So the zero crossing detection and peak detection plays a vital role. So it's very important that you understand these algorithms and where to use which kind of zero crossing detector or peak detector or even envelope detector is very important. Even in envelope detection, you typically see these things in communication systems. So these are very crucial things when you take up the applications of signal processing. Then there are some very important application in speech signals also. For example, funding the pitch or the fundamental frequency. So if you are into music, you know that some people are shrill voice, like say uh, Lata Mangeshkar, for example, has a shrill voice, and if you have a like a low pitch voice, like say Adnan Sami, so uh, using these signal processing applications like your peak detection and zero crossing detection help you to identify parameters like your pitch in the audio signal, and that helps in a lot of analysis. Now, recent research is trying to find emotion from the speech signal. It's not a recent research. There has been research on finding emotion from speech signal over the past 2 decades, and this is the one application which you can think of. And more importantly, now research is turning towards healthcare from audio signal. Like for example, if you have a sore throat, your voice signal will be significantly different than your normal voice. So if you can identify these patterns, then specifically if you can identify the pitch. So if the pitch has a variation from the normal, then you can figure out that okay, the person has something like a sore throat or cough or maybe some other issues. So these are some very interesting applications of signal processing. Of course, now people are switching to machine learning because of the availability of the data and computing power, so that you don't need to have a handcrafted features. Rather, you can extract the features based on the data. So if you have no more questions, then we can call off this session. I request the NPTEL team, IIT Guwahati, to uh, see if we can wait for some more time, or shall we call off this session? Okay, thank you very much.